Did everything post last time?
What did you want posted?
Wasn't there some homework for the rotated Smith chart?
The thing that got posted last night was homework for scattering coefficients.
All right, but the homework for the rotated Smith chart, those were posted, didn't they, before that?
Yes, sir.
All right, I'm going to cover scattering parameters today. What I wanted to do is cover or take care of anything, any kind of confusion about the rotated Smith chart right now. You got any questions about that? Because those are very important, but they're also, you can really get confused if you're not careful. You have to have a real clear understanding. Did you all do them, guys? How many attempted them? Just be honest. All right. Did you have any questions at all? No. Sorry. Go ahead. Did you or not? Yeah.
I have one.
Did you try this problem you're asking me about or not?
I looked at it and I did not attempt it.
All right. Why don't we all try this problem that was looked at but not attempted? I was hoping you tried some of these because, see, Friday's quiz is going to have these on them. And some of this stuff you're not going to get if you don't ask me now. You're probably, if you're studying Thursday night for it, you're probably going to wish you asked. There's some things that'll confuse you. I'm just leveling with you guys. All right, tell me what the problem is. Which number again?
This is 1015.
Go ahead.
30 plus 7.
This is ZL.
Yes, sir.
ZL equal.
30 plus 70.
Give me 1 second. Say it again.
30 plus J70 ohm load.
30 plus J70. You're going to need a Smith chart for this. Go ahead.
Yes, sir. And you got a 50 ohm line.
Z naught is 50.
And you are operating at 7.5 gigahertz. We need to confirm our design by calculating the input impedance.
All right, and they want an L section network, right?
Yes, sir.
All right, so first, I'm going to sketch a Smith chart. Roughly. This is the R equal 1 circle. This is infinity. This is 0. This is J1. This is minus J1. All right, so first thing we do is normalize the impedance, right? So Z normalized, let me put the steps here. It's going to be ZL normalized. It's going to be 30 plus J70 over 50. All right, that's 0.6, right? Plus J, and that's 1.4. Do you all agree with that, class, first of all?
That's what I got.
All right, now, you got to plot that. Make sure you know how to plot this. Some of that is the problem. The real part is 0.6. I know this is the 1 circle. Anything bigger than or smaller than that, when R 0.6 means the circle will have a larger radius and will be over here. It's on this side where it crosses. I'm just assuming this is R equals 0.6. Now the J 1.4 is going to be here somewhere, right about there. Right there. So now, if I look at 0.6 and J 1.4, this is about 0.1. This is where ZL is, and this would be 0.1. Can you all see that, class? It's an estimate on this thing, but you all see it on your Smith chart?
Should it be minus 1.4, J1.4?
It says J.
This is 15.
15, my bad.
It's 15. It's 30 plus J70. Is that right?
Yes.
Yeah, I think no.
Sorry. All right, you all see this? Now, let's see if you, make sure you locate this, first of all. I know it seems trivial, but people will miss this. I tell you, what I'm saying is true. They will miss this. The real part is 0.6. That's this trajectory. All right. The imaginary part is J1.4. That's this line where they crosses the point. Now, next thing you say, is it inside any either rotated or non-rotated?
out the negative.
Yes, yeah, I'm getting rid of this. That's it. Now, at this point, now I'm impedance matched. Now, when I look here, Z here is going that way. Zn is Z naught. That's what it'll be. Got me on that one, class? All right, so now we get the values. At that point, that's an impedance. Put a little Y over this to remind you that's admittance. I'm stressing this because I know a lot of people didn't do these. Come Thursday night, if you're cramming and tired, you are going to be hammered on the quiz. It happens all the time on this particular quiz. Well, I can't say for everybody. There's some very, very bright people, but a lot of people tend to fumble this one. They get confused, and especially when you're tense and unsure, you get more and more confused. Okay, now we get the values, and the way I always tell people to do this, think of impedance first, then normalize that, then go to admittance if you need it. All right, so first, this one is minus J.9. That's a capacitor. We know capacitive reactance or impedance is simply 1 over J omega C, or 1 over J is minus J over omega C. I'm going to go slow one more time on this just to really underscore this. Now, if I have that, the next thing I have to do is normalize it. Second step is normalization. So then I get X sub C over Z naught, and that's going to be minus J over omega C Z naught. We're putting an impedance. We don't do 1 over here, right? It's an impedance. That impedance has got to be equal to minus J.9. I got some questions, some people concerned they didn't understand steps I did. I'm trying to lay out everything. Y'all follow me on this, guys? Everybody see it. I'm just normalizing now. Now, I can get rid of the J's, right? And I'm solving for C. So here, I can say that C is equal to, if I take C to that side, multiply both sides by C, and then divide by 0.9, it's equal to 1 over omega, right? 1 over omega, Z naught, 0.9. What I'll see is people forget the 0.9. They'll do something that boils down to carelessness. All right, now, omega, since we got a frequency of 7.5 gigahertz, omega is just 2 pi times that, or it's 2 pi times 7.5 times 10 to the 9th. Just so we're absolutely clear what omega is. All right? Now you can calculate that. Finally, you can give me this. And let's see. I don't know if he did a capacitor first or not. But what do you get when you do this? Because Z naught on this one was equal to 50. So this should be, what, just a C1 here. Call it C1. Will be equal to 1 over 2 pi times 7.5 times 10 to the 9th. And then it's going to be times 50. And then it's going to be times 0.9. And what do you get for that? Anybody confirm that? What does he have in the book? Does he do a capacitor first or in series or not? Can you see, can anybody get the solutions? I mean, oh, somebody should email me. Does anybody have the solutions? If you could just tell me. What's that? I can pull it up too. I'll post them. Could you send me an email? Somebody, just an email, post the solutions for chapter 10. I'll post them all. I'm telling you, it's no secret about solutions. They're all over the internet. There's some paid site, was it Chegg or something like that? And there's all these other sites where kids just post the solutions for everything. They post the PDFs for all the books too.
It's either 1.4 picofarads or 1.02 picofarads.
For the first one?
This is 2.5 gigahertz, not 7.
Oh, it's 2.5?
Yeah.
Am I wrong? It was a 2.5?
Yeah, it's 2.5.
Sorry, guys. Try that. My bad. I heard you wrong, or did you say wrong?
I think I said 2.5.
Okay. My bad.
Everybody's great here.
And the answer is?
1.4.
All right, so he did a series element first. Now, for the other one, you do this with me. All right, the other one right here, that's an admittance, right? It's a positive J. Now, I know that's going to be a capacitor because a capacitor has negative J impedance. 1 over that is positive J. So, but the way I'm going to do for C2, and I hope this answers people's questions. Ali, especially, I think you had this kind of question. Some people, some other people had variants of it. I don't understand sometimes what you're talking about when it's real terse in the email. But if you can elaborate a little, I'll try to answer everything in class. So everybody on. So for the second one, it's going to be a capacitor. First, I always start with capacitive reactance, and that's 1 over J omega C. That's one of the most basic formulas you learn in circuits, right? You always go with what you know for sure. When we normalize it, X sub C over Z naught is going to be equal to 1 over J omega C Z naught. Now we have normalized it. We have to normalize it. Now once we do this, yeah.
Sorry, one question. You went from 1 to 2, that was the first capacitor?
The first capacitor takes us from here to here. Because remember, this is the impedance domain, right? Impedance, we add in series, right? And we want to go from this point to this point. We're always trying to get to the rotated circle. That's the bottom line. And that's the reason I went that way.
So if it was at the bottom and we're going up,
Well, if we're at the bottom, we'd be going this way. That's positive J.
So that'd be a conductor.
Yes,
Okay.
that's right. We can do one like that if you want, but let's finish this one up. All right, so this is normalized impedance, right? We don't want that. We want normalized admittance. We flip the whole thing, but it's normalized. I always normalize stuff in the impedance domain. Then I flip it. Now I'm going to be in the admittance domain, and now my normalized admittance is going to be equal to 1 over the normalized impedance. I'll call it 1 over ZP, and this is going to be just J omega C Z naught. And that's equal to this value right here, J.82. I'm putting in everything, so it's 0, or it's J 0.82. Now here, I casually say you see the J's go away and stuff like this. I'm going to just show you. If we go ahead and divide by J, they go away, right? The only thing we're solving for is C. So this will be C2. And when we take a look at this, that means C2 here is equal to 0.82, right? Divided by Z naught omega, or omega Z naught. And that means C2 here, and you can give me that. Omega is 2 pi times 2.5 gigahertz, right? I have 7.5, it's 2.5. 1.04 picofarad. First one was
1.141.
this one was 1.41, was it? Let me put 1.41 picofarad, and this is 1.04 picofarad. Both very small. Guys, somebody sent me a thing that had a capacitor with 0.01 or 0.02 picofarad. Was that you?
I didn't say that too.
Somebody sent me an email that showed me part lists where I could order it. Who did that? In here? I know the person's from this class because I said, what's the smallest value? I didn't think you could get values that small, to be honest with you. Apparently you can. Are we clear on this one? Allie, does this answer your question about this? All right. Now, what you wanted to do one down here? I mean, we can do them. The easiest ones are actually the ones outside the rotated circle. I mean, because you can do it either way. You can't mess them up. If you go to admittance domain first, then you can go to the admittance domain. Matter of fact, what? Oh. Anybody have a question? I want to do another one of these. And please, if you have Smith charts, give them a... Jacob, did you have a question for me? Did you send me an email? Yeah.
I've got a question on them. I gotta figure out which one it is.
Which one?
I'm trying to figure out.
Oh.
Dr. Vinsky, will there be a certain way that you'll want this done? Like, will you say, I want a capacitor in series?
Maybe.
You might do something like that?
Well, the thing is, in some cases you have no options. If they're in the rotated or non-rotated circle, if you're inside the one circle, you got to go to the other circle, right? Now, I could say I want, because that means you're going to be inside the rotated. If you're inside this one, right? Once I take 1 over that, I'm here, right?
Right.
Now, if you add, now you're in the admittance domain, right? If you add a capacitor, you go this way. If you add an inductor, you go this way. So I might say I want the parallel element to be a capacitor.
Okay.
That would limit your choices. Do you follow me on this? Huh?
Well, I'm going up or down.
Yeah, well, if it's a capacitor, you got to go this way, right? So you're going to, that way it would limit your choice. Yeah.
So what if I started in the rotated circle?
Well, what do we do? Somebody answer his question. You've been here long enough.
I know you.
If your normalized impedance lands here, what do we do, class? What's the problem with this one? If the impedance lands here, come on. If I have something inside here, right? Impedance, right? He actually had an interesting point about adding a resistor, but when you said that, the problem, you don't add resistors in this one because they take power. No power. But if you're inside the rotated, what's the problem? If that's the ZL right there. All right, if your ZL is there, suppose it's, say it's 0.6, it's on here, 0.6 plus J 0.25. All right, now that's impedance, correct, class? Listen to me. If you add anything in series, impedance, here's what you're going to do. You're moving up and down on this axis. I'm trying to show you this. No matter what you do, oh boy, you can't get to R equals 1 plus J something. All right, you have to go in row. Y'all, tell you what, let me do a problem to really bring this out. He's got some of those things. He has an impedance. I'm trying to talk my way through this, and I'm going to confuse you unless I get a specific example. You can add impedance in that one. If you're inside the rotated, inside the real circle, you can't add impedance to get to the rim of either. But if you're in the rotated circle, you can add impedance. Sorry if I didn't make that clear. We'll do another problem and really flesh that out. Can you find one where when you normalize the load, it's inside the rotated circle? Is that it? Let's do that one. This one, you're going to add impedance to it first. Not admittance, sorry.
I get it. You may have, but it didn't make sense until today.
Is it 13? Jacob? All right. Work with me on this one, and I'll try to make it clear. I got one thing to cover today, but I want to try to do problems today because this is where I can get rid of a lot of uncertainties. Go ahead and give me the specifics. First, the frequency of 13. What is it? 10 to the 9th hertz, okay. ZL is what? 10 plus J 15? All right. Z naught? 50. All right. Definitely inside the rotated circle. So I'm going to drop my Smith chart. There's a Smith chart right out there. I wish I could yank that thing in here. Okay, first step, we get normalized impedance. So ZL is capital ZL over Z naught, and that's equal to 1/5, right, plus J 15 over 50. .3. So it's really That's going to be 0.2 is like there, about. And J 0.3, so it's going to hit somewhere over here. Sorry, it's going to be inside. It's like here. It's going to be 0.2 plus J 0.3. That's not drawn quite to scale, but you all follow me? And that's ZL. So this is ZL, and that's 0.1 right here. Now, remember, that's an impedance. Can you all see it? And if you have Smith charts, can you locate that point? When you locate that point, you can see we can move two ways. Now, we're going to add impedance for this one. I didn't say that quite right last time. This one's inside the rotated. We add impedance because we're trying to get to the rim right there. So if we can add negative impedance, which would be a capacitor, we'd move down here, correct? Right? Agree? Remember, a minus J would move it this way, or we could add an inductor and move it this way. You got a preference? Either one will do. You want to move up or down? Huh? You want to get an inductor? All right. That's fine. We're going to get an inductor. So we're going to move from here to where it intersects. From here, we're going to move until we hit this, and this will be 0.2. I need that value. Where does the 0.2 line intersect the rotated circle? So that's 0.2 plus J 0.4. Can anybody confirm that?
Yep.
All right. So that's our second point. Now we're going to add a positive impedance. We were at 0.3, J 0.3. We're going to go to J 0.4. Means we're adding J 0.1, correct? So we got our load over here. Now, our first element is J 0.1, and that's an impedance. We'll get to that value in a second. Now, when you take 1 over this, the real part almost always is 1. Follow me? About 1. I mean, you're going to get 0.98, 0.97 sometimes. But if you get 0.5, you blew it. There's something way off. So if you take 1 over this, what do you get? It's the conjugate point. What is it? Anybody confirm that? Just take 0.2 over J 0.3. Take 1 over that. I trust you on that. I'm just making sure.
Yeah.
All right. Now, we're here, and we're in the admittance domain, right? We want to add something to get to this point. What has positive J admittance? Capacitor for sure, right? So then we're going to go this route, and we're going to get right to this point by adding J, and that's going to be a parallel element, right? It's going to be it's going to be plus J 0. Plus J 2. That's admittance. And then we're impedance matched. Okay? With me, let's go and try this on your own. First, that's an impedance. If I want to get the value, and it's an inductor, correct, class? So what do? We start with the impedance of inductor. That's J omega L. Then we normalize it. And set that equal to J 0.1. This should be clear. I didn't rush anything here. So what is the value of L? It would be 0.1, right? Times Z naught over omega. So it's really 5. If Z naught is 50, 5 over 2 pi times 10 to the 9th. So it looks like it's nanofarads, something small. What did you get?
79.5 nanometers.
Anybody confirm that? I'm just going to call it 79 nanofarads. Correct?
Was that inductor or a capacitor?
Yeah, nanometers.
It's in series. It is an inductor, right? Positive J.
That's nanometers instead.
Oh, nanohenries, gosh.
Both all of those should be
Is this?
Point, yeah, point, yeah. The 0.79.
All right, 0.79 nanohenries. Check that. Yeah, that's it. 5 over 2 pi, yeah. That's about right, 0.79 nanohenries. All right, that's L1. I'm sorry. Fair. Here, for the second one, it's going to be a capacitor, right? I'm going to bore you with this, but I do this for a reason. If you get it down, you don't mess it up. First, the impedance of the capacitor is 1 over j omega c. Just start there. You know the impedance. That's why I always go this route. Then I normalize it. Now I have the normalized impedance. Since we're in the admittance domain, I take 1 over that. 1 over that means I have j omega c times z naught. Now that's normalized admittance, and it's got to be equal to j2. Right? Now we calculate the value of c. So c here would be equal to 2 over omega z naught. It's 2 over 2 pi. You said it was 10 to the 9th, right? Times z naught, which is 50. And that will be the value. Really, it's 1 over pi times 10 to the 9th times 50, whatever that is. What was that? 6.4 picofarad? All right. That's that one. I want to make sure we can do it. That's one option, right? Let's do option 2 as well. Go this route. Yeah.
So you make an argument that either one of these solutions is better than the other, or are they?
I'll tell you the thing people always do is this. Anything in shunt, they want a capacitor. And here's why. Because if it is an inductor and there's a DC offset, like to the gate of a transistor or something like this, then an inductor actually like a short circuit will just short it out for DC. That's why all your parallel elements, almost always, you want as capacitors. Now your series element, it depends. If you're feeding a BJT with this, if that ZL represents the input impedance of a bipolar junction transistor, here's the deal. Well, that has to have a DC offset bias current, right? So then you put an inductor there because the DC, it has no effect on DC. It acts like a short circuit, all right? Only the high frequency would actually have an effect on. Just remember that you always want inductors in series if you're feeding a BJT and capacitors in parallel. All capacitors in parallel always when you're given an option. And the other thing is when you're feeding an FET, it's not that big of a deal. FET has just about zero, a true field effect transistor where you got an oxide beneath the actual gate. It's a metallized gate. It's just like a capacitor. So it doesn't draw DC. It does a little. There's things, this super small trickle current, but it's not appreciable. It's not supposed to be there either, but it is. All right, what I want to do is go this way for this problem, just to do it one problem both ways. All right, so we're clear? So now, things change here. I'm going to need your help on this one. That's still valid. All right. Now I'm going to go from here. That was 2 plus j.4 down to this point, and it should be 0.2 minus j 0.4. It should be the conjugate point of that if you take a look. Y'all see that, class? This is still the impedance domain, right? Here's where we came in right here. This is point 1, right? And now I'm going to move this way. Now this is impedance. If it's a negative impedance, right, minus j impedance, that's a capacitor. Correct, class? How far did I move? I started at j 0.3. I went down to j minus 0.4, correct? I added or subtracted minus j 0.7. Agreed? Everybody? So here, this is minus j 0.7. And that is an impedance. So put a little z there. Just to, if you're not absolutely confident in yourself, put a z there until you get used to it. Now, at this point, We're down here, and we take 1 over that. We take 1 over that, we're going to go to this point, and that will be 1 plus J2, I believe. Check it out.
That's what I got.
Has to be. These are always conjugate points of each other. Now, if I'm here, I got J point 2, and I'm in the admittance domain, right? To go from here to here in the admittance domain, I need to add a minus J point, or J2 admittance, right? That would be an inductor. Do you agree with me? So I know I've got an inductor, and this is going to be minus J2. Before, we had an inductor in series, then a capacitor in parallel. This is an inductor in parallel. Not the preferred, yeah?
How do we know when the components are in parallel or series?
Well, shunt is parallel, all right? Anytime you're in the admittance domain, if you go from impedance to admittance, right? Or we actually started here, so we're in the admittance domain. Anything you add in this domain, sorry, this is the impedance domain. When you start an impedance, anything you add is in series. All right? And then when you go to the other, when you go and reflect it into the admittance domain, anything you add is in parallel or shunt. Shunt and parallel are exactly the same meaning. They use shunt all the time because of a term that from electronic circuitry, when you want to shunt current away from something, you always put something in parallel. It's an old term. I guess some books still, do you still use the word shunt a lot in electronics or not? Huh?
Analog.
In analog?
Yeah.
All right. It's just terminology. Okay, let's do this. Let me call from the class. How do I get the element and value for the 0.7? What do I do? Anyone? I mean, for that minus J.7, I got minus J 0.7, and I want to get the element. So how do I do it?
You can set that.
All right, so the capacitive reactance is what? It's minus J over omega C, or 1 over J omega C, correct? Now what do we do? All right, now we divide it by Z naught, and
Equal to J. Negative.
all right, therefore what is C? C is going to be 1 over omega times Z naught times 0.7. Do you all agree with that? And what do you get for that? Can you see it back there, Allie? Jacob, is this okay? Did you have any question about this? No. You guys, what'd you get for this?
4.55.
All right. So this element is a capacitor. What about this? That's admittance because it's in shunt or parallel, correct? So I have minus J2 equal to, well, what do we say? If we have an inductor, the inductor's impedance is equal to J omega L. If we normalize it, you're going to get sick of hearing this, but you'll remember it. Normalize it, divide by Z naught. Now that's normalized impedance. We have admittance that has to be normalized. We take 1 over this, correct? So 1 over this is going to be minus J Z naught over omega L. And that is equal to minus J2. Do you all agree with me? You know, you watch, but I'm going to tell you this much. Unless you do these on your own without looking, you're going to see there's mistakes that you will make. And you won't catch them until you try these problems. And do them without looking at the solutions. Do like 3 or 4 without looking at solutions. See how many you get right completely. You're going to see you're going to make mistakes. Mark my words. So what do you get for this? You're going to get L here is going to be equal to Z naught over 2 omega. And you say it's 39 nanohenries? Anybody confirm? 3.9. You won't believe how many errors occur right here. Order of magnitude. I'm telling you, people get real casual about that and don't focus. And I'm going to take points off for that. So just telling you, don't do that. It's easy to do. I can't tell you how easy it is to do, especially when you're bored. Like they're too simple. You'll miss something simple and it'll cost you heavily. Everybody got that? Now, in the remaining time, I tried to do my best here to cover the bases. Do problems in this section. It's going to be on the quiz Friday. I'm going to give you a quiz Friday, right? Because I don't know how many people are going to miss. All right, I just don't. But on Monday, because that's Georgia game, none of you are going to be. There's going to be all sorts of problems. I hear this because of Georgia. If we win, you know, who cares about anything? My brother's coming in town. I'm going to the game. Are we favored or not?
I think they're like a 2.5 point favorite.
They're 2.5?
Yeah.
Okay, that's not much.
So yeah, it's more or less even.
Now, I don't know if this is true, but I had a conversation. Somebody told me that some of the experts believe we got a very large advantage because we rush up the middle well, and Fromm apparently has trouble with that. I don't know. I don't know if it's true. I'll listen to some of the sports shows on Thursday and Friday. See what they say.
Did you hear Harvey Updike called Paul Feinbaum since he last talked to him about poisoning the trees? This is,
He's out of prison?
he's out of prison. He hasn't paid a dime though. He was about 100,000.
Well, I would recommend he doesn't call anybody about anything. It doesn't go well. All right. Now, this is new material, so I'm going to try to make it as simple as possible. These are called S parameters. This all has to do with microwave engineering. All right, basically high frequency engineering, gigahertz on up. So with microwave engineering, most of the time we don't talk about reflection coefficients or transmission coefficients. We talk about S parameters. And here's how it works. We just set up a black box here. It does not matter what's inside here. Then we're going to connect this, and this is port 1. All right? And this is going to be port 2. Now these will be transmission lines, and it'll have some characteristic impedance here and here. And you're going to have to appreciate this, the way I'm going to discuss it. If you have a transmission line, you have both forward and reverse traveling waves possible. So what we do is we say on this port, any wave going into port 1, a voltage will be called V1 plus. It's moving in, it's got a frequency. There's also a wave moving in the opposite direction. That's called V1 minus. That's coming out of the port. Now over here, this is port 2. You're going to have a voltage moving this way that is called plus V2. All right, it's moving that way. And he always puts these squiggly lines to indicate it's a wave. And then we have something moving out. It's V2 minus. Now, remember, that voltage is developed from here to here. But one is a positive traveling wave in this direction. The other is a wave traveling in the negative direction, if you will. Okay? So the relationship between the S parameters is this. And this is called a two-port system because there are only 2 ports. There are 2 ways, really 2 ports of entry. You've got 2 transmission lines connected to, one connected to the front, the other coming out the back. All right? Here's the relationship. V1 minus, this is coming out of port 1, is equal to S11 V1 plus S12 V2 plus. Then V2 minus is equal to S21 V1 plus S22 V2 plus. All right? The way this is usually written is just V1 minus V2 minus is equal to, and then it's S double bar, usually that way, V1 plus V2 plus. Now what that allows you to do is take an inverse of this matrix and say if you have these values, you can get those values by doing 1 over that S. And what is S? I'm putting a double bar over there, but you don't have to. That is simply S11, S12, S21, S22. That's all it is. These are called scattering parameters. Has anybody used S parameters here? This is how all high frequency work. When they characterize amplifiers, this could be an amplifier in there, anything like that, or filter, it's always with S parameters, always. A lot of times they're given in dB, but it's very common and you see it everywhere. Now, when you have S parameters, the first thing you got to do is learn how to calculate them. You can't design anything until you realize how to actually go through an analysis. So if we take a look at S11 for a second, right here. Well, if I make V2 0, V2 plus 0, then S11 is V1 minus over V1 plus with V2 plus equal to 0. It means there's no possible wave going this way. All right? In other words, there's not a short out here where you'd have a wave hit and come and reflect back in. You follow me on this? In other words, if you just have Z0 out here, then there's no reflected Z2. Now, if you have just Z0 out here, all right, and the internals of this don't have any possible reflection, and I'll get to that, then this is just a reflection coefficient. You can make a note of this. This is, a lot of times, a reflection coefficient at port 1 if V2 equals 0, V2 plus is 0. That's not always the case, and I'll get to examples of that. When I take a look at S22, it's the same thing. It's V2 minus over V2 plus, provided V1 plus is 0. And that's just like the reflection coefficient on port 2 if V1 plus equals 0. So I'm trying to make you draw parallels to stuff you already know. Reflection coefficients are things you understand, right? Reflection coefficient has to do with the ratio of the reflected wave to the incident wave. Now, the other two are transmission parameters. And if you look at S21, right here, you can see that's V2 minus over V1 plus if V2 plus is 0. Let me elaborate on this. This is called the transmission or the forward gain. And here's why. V1 plus is a signal coming into this, right? Now, if it's an amplifier, just assume the output voltage is amplified by A, right? Then V2 minus would be A V1 plus. Do you follow me on this? And if you took the ratio of V2 minus over V1 plus, you would get A, the amplification factor. Do you follow me? So this really is the forward transmission gain, or the amplification of the incoming waveform. That's a way of thinking of it, all right? It's not really that. There's more to this, but in the pure sense, if this was just if we put this into a FET amplifier right there, then that would be the case, would be the amplification factor. Got it, guys? That's the way I think about it. By the same token, S12, I'm not sure if they use this. Do they use S parameters in analog? They used to. The H parameters, S parameters, which you use? Use S? H parameters? Well, yeah, H parameters are similar. We can get S parameters from them. But for this, here it's going to be V1 plus over V2, or I mean V1 minus, pardon me, over V2 plus with V1 plus equals 0. This is the forward gain. Write this down. This is most of the time called forward gain. And this is usually called reverse gain. Dr. Wentworth used to build a lot of microwave amplifiers. I don't know about now. This is the common terminology that they talk about. They talk about scattering parameters, forward gain, reverse gain, or sometimes they call it they almost never use the word reflection coefficient, but S11 generally is that. They'll talk about the forward gain or the forward transmission gain, something like that. All right, now the best thing to do is, when I'm out of time, is show you a simple example. And I'll do as simple as possible real quick. Am I out of time or?
Yes.
All right. Then I'm going to go through this. I'm going to give you problems on this one. I guess they're up. The scattering problems? Yeah. Look at the examples. They're laid out. The trick is this. You have to get the transmission coefficient and then the voltage division after that. I didn't have time to go through that. Look at the properties. Some of these things there's a little subtlety in these, all right? But please look at the examples. And we'll see you. It's not going to be bad, but it is on the rotated Smith charts. If you want to bring your own, please do it. I'll provide some, but it's much better to bring the ones you feel comfortable with. And try. What's that?
Will it be the regular Smith chart one you're providing, or will it have the?
Rotated too, absolutely. Because you know it's hard to estimate that exactly.
It is.